Hey, students, I got another great question here from number 27. And if you haven't seen the example I did for number 4, you might want to see that one. Although I guess it doesn't really matter which order you put them in. But just trying to get the gist of Faraday's law conceptually is a bit of a challenge. And I did number 4, and then at the end of number 4 kind of alluded to this one. And this one's got some interesting pieces here. So let's read this, and I've printed out the picture here. Oh, and I should put up here, this is from chapter 23. So chapter 23, number 27, it says this. It says, a coil is moved through a magnetic field as shown in figure 23.59. The field is uniform inside the rectangle, so in here where they kind of show a field, and they put little dots coming out, and 0 outside. Okay, so like out here would be 0 field, outside here would be 0, I guess here and here, but that doesn't really matter. So it looks like it goes from no field into a field, and then back outside to no field. Okay, what is the direction of the induced current, and what is the direction of the magnetic force on the coil in each position? All right, so it's a two-part question, because one is the direction of the current, one is the direction of the force. But it is also at 5 different locations, A, B, C, D, and E. So let's start with A. And if you let me draw kind of a coil here. And the coil has not quite got to the magnetic field. B looks like where it's transitioning. So in A, what we would say is there is no flux going through it, and as it moves along, there still is no flux. So that means there would be no change. And remember, the induced current is created to oppose any change, but this doesn't have a change. So I would say there is no current, and so I guess I would say I equals 0. Again, Faraday's law says you're only going to get a current if there's a change. And so there's no current. And then for that matter, there would be no force, because that whole force on a wire that has a current, so this is the wire of length L with a current in a magnetic field, would have a force from the previous chapter. But if we don't have any current, this just comes out to be 0. I mean, it makes no sense to even talk about a force if there is no current. You have to have the currents and the magnetic field in order to have a force. So it's kind of boring, but important to realize here that you must have a change. So I think that's what the author is getting at. Now, for that matter, maybe I should also say the same thing is happening at E. Because as you kind of go all the way through here at E, you can see it's already on the outside. There is no flux, and it continues to move. Again, there is no flux. There is no change in flux. And so I guess I would describe E and A as the same thing. No current, no force. What's kind of interesting, though, and don't want you to miss, is that C is actually the same as A and E, because in C, the coil is fully in the magnetic field. Maybe I'll kind of color it in, but there would be a lot of flux. So in one sense, C is different than A and E, because A and E has no flux, but C does have flux. But again, this is where I want to emphasize, Faraday's law is not about opposing the flux. It's about opposing the change in the flux. So our attention needs to be on the change, not just what is its value, or is it up or is it down? It says just does it change? And so that's why I'm going to say that C is actually really the same answer as A and E, because in C we have a lot of flux. Let me just, for the sake of, give a number. say it's 10, and the little dots say it's out. So I would have a flux of 10, if I want to use a fancy word, 10 Webers coming out. But as it moves along, it still has 10 Webers in it. You might say it's completely filled. The ring here is completely filled, and as it moves along, it's still completely filled. So it was 10 here, it moves across, it's still 10, it moves a little more, it's still 10, a little more, it's still 10. It's not until it begins to exit that it loses flux. Or back here when it was entering, then there was a gain in the flux. But when it was completely outside, both left and right, but also here at C, where it is completely submerged in the flux, and as it moves along inside, it's always 10. So there is no change. And if there's no change in flux, there's no induced current. There's nothing to talk about. And no current means no magnetic field. So that's a big step here, I think, in this one, is to realize you have to have change. So that's why we can hopefully quickly say A, E, and C are really the same thing. They have no change in flux and therefore no current, and no current means no magnetic field. But of course, what that also means then is B and D is going to be a little more interesting. B and D is going to have a change in flux, and then is going to have a current, and is going to have a force. So B, as if I can use my fingers on your screen, is transitioning in. And so when it's outside over here, there's no flux. And as it's transitioning, it's increasing, and gets up to its full value, which I called 10. And then it stays 10 all the way across. All right. So I would say that the flux, and I'll use that fancy word primary. And so here's my coil. The flux at first is 0, then it's maybe a 1, and then as it moves more in, it's a 2, it's a 3. So it's going from 1 up to 2, up to 3, and again, I'll just put 10, and it's out. So since before it came in it was 0, as it starts to come in and the primary makes 1 out, the current is going to be set up, what I'll call the secondary, to make 1 in. And so I'll do that in green and say the current in this coil is going to be set up in such a way that it'll make the flux go in. And using right-hand rule number 2 from the previous chapter, I'm going to put my thumb into the screen, and you can see my fingers curl around in a clockwise direction. And so B definitely has a current, and it is in a clockwise direction. Now let me also do something else here. If I kind of imagine the coil halfway in, and so this red box I'm kind of drawing is where there is this primary magnetic field. I want you to see that the current, although it's around the full coil, only has a force on the right-hand half, because, see, this left hand doesn't have a magnetic field. Remember this formula we were talking about back in A and E and C, is that in order to have a force on a current, it must be in a magnetic field. So this coil has a current all the way around it, but the left side of this coil is not within the field. So there's no force to think about there. We just got to think about how much force is on this part. And maybe to kind of overly simplify it, I'll draw it in black. Let's just think about the current then as going down as opposed to having a little bit of an arch to it. but it would be down. And so to get the direction of the force, we need to do this vector cross product, which we called right-hand rule number one, right? And then, let's see, I'm used to doing this one, but I think you guys, your author seems to like the one where he says, hey, put the first vector, your direction of your thumb, the second vector, the direction of your fingers, and then your palm is the direction of the force. So this would be the direction of the currents, L. So let me put my thumb in the direction of the current. My fingers then need to go in the direction of the B field, which is out of the screen. Okay, so my thumb's going down, that's the current. My fingers need to come out of the screen, so I'm going to point them into the camera like this. And then my palm is pushing over here to the left. So that would tell me this is creating a force to the left. You might say it's actually opposing it entering the magnetic field. And so if you actually do this, and I think I did that electromagnetic braking as a demo in the lecture, where I had a piece of metal and it swung into a magnetic field, and then it opposed a stopping mechanism. It's an electromagnetic brake. Those of you who use hand tools like a drill on a battery pack, those are really kind of nice because you'll be pulling the trigger for the drill. Maybe you're driving a drywall screw, and your better drivers, as soon as you take your finger off the trigger, it actually makes another connection, which makes a current through the magnetic field. The same magnetic field that was being used to generate the motor now generates a current and then uses that as a brake. And so you're using your power tool and you're drilling along, and it just stops. I mean, it just comes around and stops. And it's really nice because then you can just, drive that screw to the right depth you want. And as soon as you take your finger off, you got just a quick break. It doesn't drive the screw deeper, especially into drywall that you wanted. So anyways, this is the direction. And I think that was the other part of this question. So what is the direction of the magnetic force on the coil in each of these positions? Okay. And D is kind of interesting here. So let's talk about D. Maybe I'll draw the coil a little bit over to the right here. And maybe I'll do the same kind of thinking that I'll make a red rectangle here, kind of showing as it's leaving. But let's start with, answering this question. What is the direction of the current? And so you'll need to remember that before it started to exit, it was actually in the magnetic field. And so over here, I'll just, for the sake of a number again, put a 10, but it's 10 out. And so as it begins to exit, there's less field. So maybe it goes down to a 9, maybe it goes down to an 8. But remember, Faraday's law says it opposes the change. So since we're dropping down, we would want the flux to be pointing out, and the flux would be in the secondary. We would want the current set up in this coil in such a way that it would make flux to come out. That is to keep it at a total of 10. Because as we're leaving, what I'll call the primary field is going down. Therefore, a current is set up in the secondary to get it back to 10. And so that would be coming out. See, that's kind of the exact opposite, but the same physics that we said here. Here we were at 0 and increasing, coming out, increasing. So we wanted a secondary going in. That was opposing the change. But here, when we oppose the change, we want to keep the flux in the same direction. So let me say it again. Notice I am not saying it opposes the flux. The secondary is not opposite to the primary. it opposes the change. So if you have your primary dropping, the secondary will be in the same direction. And watch my video on number 4 for part B on that one, where it's a decrease. And then likewise, also here, if the primary flux is increasing, then the secondary will be opposite to that to keep it the same. And then it does oppose the flux. But it's really opposing the change. And so don't use the phrase it opposes the flux, because you'll always think that the primary and secondary have to be opposite in direction. And they don't. And this right here, this last one, I'll call it the hardest one, D, is really an indication of that. Okay, so I'll say it again. As it's exiting out, the primary flux goes down. Therefore, the secondary is in the same direction as the primary to keep it the same. It opposes the change. So if we go back a chapter to our right-hand rule and notice that the current in this coil has to be in such a way that the flux comes out, I'm going to take my right hand and put my thumb up. And so looking at my fingers, it will curl around in a counterclockwise direction. And so there's the answer to D. And maybe not a surprise that they are opposite. So as it enters, the current is induced in a clockwise direction, and as it exits, it's a counterclockwise direction. And in these other cases where it is either not in it, which is A and E, or fully in it, which is C, there is no change and therefore no current. Now, one last step here is the force. And I'm going to do the same thing here in D that we did in B. Let's use this equation, the Lorentz force, if you will. And we need to know the direction of the current and the direction of the magnetic field. And I'm going to kind of do the same thing. That I'm going to say that, okay, now that we've learned that the current is counterclockwise, the left side of this current is going down, whereas the right side is going up. But I won't pay any attention to that one because the right side now has no field in it. So there would be no force. So it's only the left side of the coil that's going to have a force in it. The right side doesn't. And so using right-hand rule number 1, I'm going to put my thumb in the direction of the current, okay, and my fingers in the direction of the field, and maybe I should say the primary field, although I guess in this case the primary and secondary are in the same direction. And then notice my palm is to the left. And so the force is left. And back in B, I didn't write it, but we said the same thing. The force is left. And you might have thought that the force was going to be in the opposite direction because here the current went clockwise and here the current went counterclockwise. But we also changed left and right for the currents in the coil. And so you might say from looking at B to D, there were 2 negatives. We have a negative because we're looking at the force on the other half of the coil, and we have the negative because the current changes direction. And so if you take the negative and then the negative again, you're back to the same direction. So not too surprising that it opposes it again. It's a left. And so these rings, if you ever get a chance to play with them, are kind of neat. They make good electromagnetic breaks because if you enter a magnetic field, there's a braking. And then when you exit, there's a braking. And so it opposes the motion as well. Some people even misstate Faraday's law and say it opposes the motion. And that's not really what Faraday's law says. Faraday's law says it opposes the change in flux. Now, if you're only interested in motion, you can say, oh, it opposes the motion, therefore when it enters, it slows it down, and when it exits, it slows it down. And that would work if that's all you're trying to do is to find opposing the motion. But a lot of times we want to know the direction of the current, and we can't just get there by saying it opposes motion. We need to say it opposes the change in flux. And so there's more to Faraday's law than just opposing the motion. But it always does oppose the motion. All right. Well, hope that wasn't too long-winded, and hopefully that was helpful, and good luck studying. Bye.